let's do some more calculus. Whoop whoop. Okay, so this is only daily lesson 168, 169, which I'm sure is welcome after the last one. But here it has numerical approximation. This was all the stuff we did with drawing those many rectangles before. These are all approximations. So you can take this and you can copy them down, or you could flip back and forth from your previous pages into now and then copy it down that way. But I have it here all for you on one page. So write that down. Okay, now what we're going to do is look back and think about whether this would be an over or an under approximation. So I'm going back to even the very first one we did. This was a Riemann sum. This is on 158. This was a left-hand Riemann sum with a length of 2 units. So 1, 2, each of these bases was a length of 2 units. And I can see that right here, if we're talking about the area under the curve from 1 to 6, and this area is all here, these boxes, this rectangle is missing some right here. But it's over approximating the area here and here, which would take more than this space. So I would say that this first one is an over approximation. We're going to do the same things for the other ones. If I do this one, I can see that there's missing some area here. There's a lot more over here, and I can see more and more. So this one, I would also say, is an over approximation. What would you think about this one? Over or under approximation? Meaning, is there more area in those rectangles than in the actual region itself? Or do you think there's less? I think over. It looks like it's missing some areas right here, but it's covered over there, and there's even more here. So over approximation so far. If I keep going, here we start getting into the right Riemann sum. So the left-hand Riemann sum was over. But once I get into the right-hand Riemann sum, I can see that this looks like an over approximation right here, but then it's under and way under right there. So I would say that this one is under, and possibly, because of this area, way under. Okay, let's do the other ones. So what do you think about this one? Over or under approximation? What do you think about this one? Over or under approximation? What about this one? Over or under approximation? And really, we're guessing here. How about this one? Over or under? And now we're getting into trapezoids. What about this one? And this trapezoid, do you see how this looks closer to the shape, but I'm still missing a little bit of area here, a little bit of area here, and a little bit of area here. So I would say this one would be an under approximation. This approximation, it looks pretty close to me. But if I could zoom in on this, which the only thing I've got right now with the technology is going, ooh, and that doesn't really help because it's just me drawing it. This is a curve, and so if I have a straight line from here to here, there's going to be a little bit of area in between that straight line and the curve. Same thing here, same thing here, same thing over here, the whole way down. So even though this one is incredibly close, I would still say this is an under approximation. Okay, so to check this, anything over 40 is an over approximation. Anything under 40 is an under approximation. I know if you didn't get that, if you thought some of them, they're like, oh, this could be really close, I'm not really sure. That's okay. I just want you to get an idea, and just for the sake of the chart, I'm telling you anything over 40 is over, anything under is under. Over here, we're going to fill this in during the next lesson because there is a way to get the exact area without doing all of that work we just did. I know you might be yelling at the screen right now because you drew a lot of rectangles. That's still important because even though you won't have to draw lots and lots of rectangles again, what you will have to do is stuff like this. This is the type of application you'll see for Riemann sum. And it doesn't look the same, but it should help you still like visualize what is happening at each one of these because you did all of that work before. So kudos to you. Good job doing the work and putting in the time so that you will understand this better now. This one says approximate this integral from 0 to 25 of f of x dx. What that means is whatever this function looks like, the area between f of x and the x-axis. So sometimes that might be above the x-axis, sometimes below. Anytime I have a number, a function value below the x-axis, I'm still going to go with that. Area above the x-axis is positive, below is negative. And we'll do more with that later. I know the only thing we've seen so far has been positive area above, but any area below the x-axis is going to be negative. So for instance, if I had a function that looked like this, oh, it's kind of hard to see, and there was the same area above as below, the total area would actually be 0 because some is going to be positive, some is negative. We'll talk about this much more later, but for right now, we've just got this table, and I just wanted to make you aware you don't change anything with these negative values. We're still using them. Okay, this says find the integral from 0 to 25. So I'm just looking at the table. 0 the whole way to 25. I'm good. Okay, I have to use the entire table. There's not some of it that I'm ignoring. It says using a midpoint sum. So think about it. We're talking about rectangles here. Rectangles. Using 3 subintervals. This means we have 3 rectangles. So we're going to find the area of 3 rectangles. And you're like, how do I do that? 0 to 25. I'm going to tell you in all the other ones we did, the base was always the same. It's not necessarily the same here. So I'm going to split this up the best I can. So 3 rectangles, I'm going to say, well, from here to here is 1 rectangle. From here to here is another. And from here to here is another one. I know it seems strange because I'm kind of making part of the base, but it's just saying, here's 1 rectangle, here's the next one, here's the next one. And just like in our picture, all the rectangles were touching. So you can see right here, it was like, well, this is a trapezoid, but it's touching, and I'm using the side. I'll show you a rectangle. There we go. All of my rectangles were touching here. From one to the next, same idea here. That it's going to go from 0 to 7, then start the next rectangle is going to go from 7 to 15, then 15 to 25. So let me get a rectangle with a midpoint sum. Okay, so for instance, this one. This was on page 165. And what we did in all of these rectangles, these all had a base of 1 from here to here, from here to here. So it was the change in the x value. That's why we had this 1 out here. These don't. From here to here would be 7. So my base, if I'm thinking base times height, the base of the first rectangle is 7. The base of the second rectangle would be from 7 to 15. That's a change of 8 times my height, which I'll figure out in a moment. The base of my third rectangle, so again, I'm thinking about base, like what's the distance between my x values, would be from 15 to 25, 10. So in everything we've done so far, we've had the same width of each rectangle. Not so much right here. We just do the best that we possibly can. So I split this up into 3 rectangles. This was 7, 8, and 10. That's the distance between the x's. If I'm thinking about a rectangle, I find the area by saying base times height, or length times width. In a midpoint Riemann sum, let's think when you are drawing the rectangles. This was my length, or let's say the very first triangle, silly me, very first rectangle. The base was 1, but how did we figure out the height? Well, we went up, for a midpoint Riemann sum, we went up halfway. We went and found the function value at 1.5. So here what we're going to do is find the function value of whatever this middle value is. So 0 to 7, the one in between, even though it doesn't have to be exactly in between, would be just the function value at 4. Or I could say 7 times 6. Okay, so what would be the function value f of what for my next rectangle? Would it be f of 7, f of 12, or f of 15? This is a midpoint sum. Yeah, it would be f of 12. So if I'm talking about the length of the rectangle or the base, that'd be 8. The height would be this seems strange. I could have circled this before too, because this is my midpoint. The height would be -10, so below the x-axis. In the last one, the base would be 10, because the difference between 15 and 25 is 10. I would use times 8, or I could say f of 20. This is an x value, this was a y value, or the distance between the x's, this is the y value. So I'm going to say 10 times 8. And then from that point, easy peasy lemon squeezy, you're just figuring out what these numbers are, which, looking back at old me, oh, there. Okay, so the last part, easy peasy lemon squeezy, we're just taking all of these and multiplying them together. So 7 times 6, 42. Plus -40 would be +2 still. Plus 80 would be 78. That's not what old me said. Hold on, what did I mess up? Oh. Okay, so from this point, easy peasy lemon squeezy, we just need to multiply these things and add. 7 times 6 is 42. Minus 80 plus 80 would still be 42. Whoop, whoop. We just estimated this integral because it's the area under the curve from 0 to 25, or I could say the area between the curve and the x-axis. Okay, let's do another one. This one says approximate from 0 to 15. So the integral from 0 to 15 of f of x dx. We're going to talk about this more later, but really this f of x, this is a y value, this is the change in x. Notice in that last one when we had a y value, this was the change in x. Interesting. If this only says 0 to 15, the first thing I would do is get rid of this part of the chart. Don't even use it. And you don't want to think, oh yeah, I should leave this in there. A left-hand sum. A left-hand sum was when one of the first ones that we did. So let me get one of the left-hand sums. I put these all out of order and I shouldn't have done that. The very first one we did, where in every one of these we did my x, my change in x, so down here this was 2, times my height, and I used the function value on the left, like the most left for a Riemann sum. So here I'm going to go in, this has 4 subintervals. So break this into 4 rectangles, or 4 parts, into the table into 4 parts. 1, 2, 3, 4. It's okay that these are all different. This, the distance between 0 and 4, is 4. So I'm going to say 4 times. Now I'm going to the left. So if I find something to the left, that would be f of 0. Or I can see here when we started our integral at it was from 1 to 7, we said f of 1. Same idea. So I'm just going to write 4 times 15 plus 3 this time, times 6, because that would be the left, plus 7 and 12 will be 5. My function value on the left would be -5. 12 to 15 has only a width of 3. My left-handmost value would be -10, and I stop there. If you wanted to graph this, you could, but I think it would make it more complicated. If you want to write 4 f of 0 plus 3 f of 4 plus 5 f of 7 plus 3 times f of 12, go ahead and do that. I just did, I made sure this is an x, the change in x, my y value, change in x, a y value, change in x, a y value. And these are always the left-hand sum, so I'm using in my rectangle on the left. Okay, so I want you to use what you've learned so far and think about, could you go through this on your own? I'm going to go through it step by step, so if you need to follow, do it. If not, try to do this on your own. Make sure you pay extra attention to the 4 to the 20 to cross out anything that you don't need. Okay, let's do this. So 4 to the 20, I don't need the 0, 15, and I don't know the 25, 20. So get rid of that. This says a right-hand sum. Okay, so I know the function value I'm looking for is on the right. There are 4 subintervals, so I'm breaking this into 4 parts. 1, 2, 3, 4. I have 4 rectangles. Here's 1, 2, 3, 4. The distance between 4 and 7 would be 3. So that's my x value. A right-hand Riemann sum, I'll be looking at the right hand of the rectangle. So the function value on the right. Between 7 and 12, on the right would be -10. Between 12 and 15 is 3. On the right would be -2. Between 15 and 20 is 5. That's change in x value of 5. On the right is 8. And silly me, I realized that I just didn't give you the answer on the last one or in this one. In this one, if you multiply all these things out and add them up, you should get 23. In this one, you should get -31. Okay, let's do one more. Okay, this says go 0 to 25. That's nice. The integral from 0 to 25. I'm using the entire chart. Trapezoids. What? It sounds like I'm saying like a really nerdy swear word. Trapezoids. Oh, trapezoids. Actually, please, instead of swearing ever, start using that. Oh, trapezoids. That'll be a good one. Okay, anyway, trapezoidal sum, 0 to 25. Remember that finding the area of a trapezoid is 1/2 base 1 plus base 2 times height. Or you could say base 1 plus base 2 divided by 2 times the height. I'm going to go back to a trapezoid when we drew this before and kind of remembered what the base 1 and base 2 were. But first thing I'm going to do, if this is 3 subintervals, I'm going to break it into 3 shapes. And remember, they're going to be touching each other on the ends. So where one lets up, the other one starts. So 3. So this would be 0 to 7, 7 to 15. I want to divide it into the appropriate number of the squares that are there, not worry so much about the numbers and dividing evenly that way. Okay, so I have 3 different trapezoids I'm going to do. And I know I have 1/2 base 1 plus base 2 times whatever the height is, and then do the same thing for the next 2. Well, if we go back to, I think it was like 167, but let me make sure. Oh, it was 166. On the top of 166, I drew this, where I have the area formula, and then I said traditionally we think about base 1 and base 2 being the x values, like, or the base, and that's where they're parallel. In this one, it's going to be the height. So it's, well, and I shouldn't quite use that word. It's going to be parallel still, but they're going to be 2 function values for the base, and then the height is actually going to be laying down, which is okay as long as the height is perpendicular to the base. So knowing this, I'm going to put this actually right there so you can see it. Move this over a little bit. If I'm talking about 1/2 base 1 plus base 2, this was a y value and a y value. So I need to do a y value and a y value. 15 plus -5. My height is going to be the change in x this time. So the change in x is 3. Okay, you fill in what's base 1 and base 2 on the second trapezoid. I use this -5 again, -2. The height is going to be change in x. Okay, completely try the last one. Base 1 is negative. Ooh, so sorry. Whoa, 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 whoa. Did I forget something? In the second one, you have 1/2 base 1 plus base 2. And I forgot to write it. Whew, fixed it. Okay, so in the second one, you've got 1/2. This is the base 1 plus base 2, coming from the y values. The change in the x is the height. That's the 8. In the last one, you try. -2 plus 20 be the function values. The height will be the distance between the x values. Okay, do some work here. You'd have 1/2 times 10 times 3, so it would be 5 times 3 plus, we're just doing a little bit of this. This would be -7 times 8 divided by 2, so -56 divided by 2. This would be 18. 1/2 would be 9, 90. 15 minus 28 plus 90. 90 minus 30 would be 60, but that's not it. So 62 plus 15, that's not, hold on, something's wrong here. Let me check this one again. Oh, silly. Crap, I made a mistake. So you see right here, the distance between 0 and 7 is 7. I'm just modeling, you know. Check yourself just in case you wrecked yourself. And then fix it. Okay, so this would be 35 minus 28 plus 90. There we go. Okay. So this is always the base 1 plus base 2. The height is the distance between my x values, which would be 7. Thanks so much. Bye. I think you're awesome.